Hi boys and girls, hi Varsha and Vidya. In the last presentation and video you have understood the different digital modulation schemes such as ASK, FSK and PSK. You understood the waveforms and you understood the significance of the Bpsk modulation and its importance in mobile communication. So in this video we will see in great detail the mathematical model of Bpsk. We will see some demonstrations with Python, especially the effect of the AWGN on signal constellation, and we will derive the probability of error. So with that basic introduction, let me invite you all to this presentation. So the objectives are you will learn the mathematical model of Bpsk signal, and then you will understand the Bpsk signal constellation, that is a vector representation of the Bpsk signal, and the effect of AWGN on that. I will give you some demo of the Python codes for that, and you will derive and understand the probability of error. So ultimately what a digital modulator does is, I told you, if you consider as a black box that is receiving bits or streams of bits into it, and it is converting them to sinusoidal waveforms for ease of transmission through physical channels. So in phase shift keying, the phase of the sinusoid is varied in according to the bit pattern. In the case of the binary phase shift keying, the phase of the carrier is shifted by 180 degrees when a signal transmission or a bit transmission occurs. So for example, a logic 0 is mapped onto the symbol e raised to j0, which is nothing but 1, and a logic 1 is mapped onto e raised to j pi, which is minus 1. So the idea is, if a bit 0 is there, here also we prefer to use bipolar signals, like logic 1 is marked as a plus 1 and a logic 0 is marked as a minus 1. So if a 1 is encountered, it is mapped on to minus 1, so that's e raised to j pi, and a minus 1 is mapped on to 1, e raised to j0. That is how the Bpsk mapping is done. So just for your ease of remembrance, let me go back to this waveform. So this is a bit 0, that is this red curve. The red signal shows the bit pattern, and the blue curve shows the Bpsk output. So here, from here 0 to 100 nanosecond, that is my low signal, which is a minus 1. This is a bit 0, which is represented by minus 1. Here the phase of the signal is 0, and when at 100 nanosecond the bit becomes 1, which is a logic 1 or plus 1. So here the signal reverses in phase. So an additional phase of pi is added to that. Again there is a 0. Again there is a phase change. So this is how the Bpsk signal has to come out. Now if you come to the mathematical model of Bpsk, what is this? Basically this cosine signal. So what is happening? How do I achieve this phase reversal? Here I have to multiply by a minus 1. Okay, the signal is coming in this way. This is multiplied by plus 1 into this is some cosine function, some cos 2 pi fct. This is multiplied by plus 1 here, and here there is a phase reversal. So here I have to multiply by minus 1. So what I am ultimately doing is I am multiplying the bit pattern with some cosine function. This is my bit pattern bt or bit. There are two cases for I equal to 1 and I equal to 2, corresponding to S1 and S2. Okay, so because I have to transmit two waveforms, S1t and S2t, corresponding to logic 0 and logic 1. So I variation of I is from 1 to 2, S1 and S2. Okay, so likewise, what is B0, BT, BIT has two values, either a logic 0 or a logic 1. Logic 0 corresponds to -1 and logic 1 corresponds to +1. So when I multiply, when the bit BT is a 1, this goes into root of 2 EB by T cos 2 pi FCT into 1. If it is a -1, if the bit is a -1, then SIT is a minus root of 2 EB by T cos 2 pi FCT. Now, to understand it as a vector, you can slightly manipulate this like this BIT into root EB into root of 2 by T cos 2 pi FCT. If you look at this term, if you look at this term, root of 2 by T cos 2 by FCT, that has a unit energy. Because if you integrate, if you compute the energy of signal cos 2 by FCT from the duration 0 to t, that will become root of t by 2. So when I divide the cos function with the root of t by 2, it has a unit energy. And what is this capital T? That is the bit duration. Here if you say the capital T is 100 nanosecond. Here the duration is 100 nanosecond. So capital T is the bit duration. That's 100 nanoseconds here. So I will explain this term again. That's BT. BT is my bit pattern. That is either a +1 or a -1. If it is a +1, corresponds to a logic 1, it is plus root 2 EB by T cos 2 pi FCT. If bit is a 0, it's a minus root 2 EB by T cos 2 pi FCT. All this is during the interval 0 to t. Here in the last picture, this capital T is a 100 nanosecond. So I rearrange this equation so that it comes in I can put this signal in the vector form, so that this root of 2 by T cos 2 pi FCT is my basis function, or my orthonormal basis function phi 1t, because this has a unit energy. You can do on with a pencil and paper. You can compute the energy of the function cos 2 pi FCT from 0 to t. You will see that it will be root of t by 2. So a multiplication by root of 2 by t makes this thing a cosine function with unit energy. So this root of 2 by t cos 2 pi FCT is nothing but my phi 1t. We learned this in Gram-Schmidt procedure. So ultimately this signal SIT becomes BIT into root EB. What is this root EB? It is the energy of the bit in the interval 0 to t. That is a bit duration. That is the energy of the bit during the bit duration. So it is BIT into root EB into phi 1t. Okay. You can see that there is only a cos function in this, so there is only phi 1t and there is no phi 2t. Okay, it's just like if you look at equation 1, it is just like 2ax, as we see in geometry, 2ax. Okay, so 2 is nothing but it is equivalent to root EB here. Ax is equivalent to my phi 1t. Okay, or phi 1t is equivalent to my ax, and root EB is equivalent to my 2ax, if I say. And BIT, it can be either a positive sign. In one case, it may be a 2ax, or if it BT is a 1, or else it will be a minus 2ax. Now, if I take these two cases, like if these bits are plus or minus 1, if the bit BT is a 1, S1T is plus root EB into phi 1t. Or else, if the bit is a minus 1 or a logic 0, that is S2T is minus root EB into phi 1t. Now, I got these signals as vectors. Only one orthonormal basis function is there, phi 1t, just like I have a vector in the totally lying in the x direction, 2ax. Okay, there is no ay component. Likewise, here there is no phi 2 or phi 3 components. The signal lies along one axis. So if I plot this S1t and S2t against phi 1t, I get the signal constellation of Bpsk. So that is here. So this is my phi 1t axis. Okay, this is from this phi 1t is nothing but root of 2 by t cos 2 pi fct, and this is my origin. This is origin. If it were a signal with phi 2t also, I would be having an axis along this, but there is no such axis, or no phi 2t or phi 3t. So the signal lies entirely along phi 1t. And what are these signals? One is happening at plus root EB into phi 1t. This is equal to 2ax. This is equal to minus 2ax as in geometry, as in vector algebra. So here, if I come here, so I have one point here. This is a point S1. That is a vector S1. This is corresponding to the signal S1t. This is from here, from 0, this is a distance of root EB. And this is my signal, this is the vector corresponding to the signal S2t. These red dots, these two red dots corresponding to the signal vectors. This is S2t, this is corresponding to the signal S2t. This is separated from origin by a distance of minus root EB. And that is here. It's very simple. So the two signals S1t and S2t, they are transmitted. They look like this. The vector representation looks like this. Okay. How do my receiver receives that? When it receives the signal, it checks whether the signal is positive, that is above 0. If it is above 0, it says S1 is transmitted, or a logic 1 is transmitted. Or if the signal is negative, you can my receiver will take a decision that it is below 0. So originally S2 is transmitted, or the logic 0 is transmitted. So this is the importance of the Bpsk signal constellation. Now we will demonstrate this with Python code. Now, if I come here, I use the simple Python code for demonstrating this signal constellation. And before I go to that, let us see the effect of noise also. Let me go back to this presentation and let us see the effect of noise. Now consider that I transmit this baseband Bpsk signal through an AWGN channel. And I told you the importance of the additive white Gaussian noise channel, why it is Gaussian, why it is spectrally white, and why it is additive. I told you all that in the previous videos. Now, when I say it is spectrally white, the post-spectral density follows a pattern like this. For all frequencies from minus infinity to plus infinity, this post-spectral density SNF remains constant at n0 by 2. Okay. This is a standard convention to write it as n0 by 2. Okay, and this is spectrally white. We generally believe that it is spectrally white. Okay, for all frequencies from minus infinity to plus infinity, the power spectrum stays the same. It stays flat at n0 by 2. So this is the noise power spectral density. So corresponding autocorrelation function will be n0 by 2 delta t, which is a delta function. So with that prerequisite, let us see what will happen when I subject my signal constellation to noise. So what I do initially here is I generate some, say, 1000 random bits. Okay, so I use this code sin rand n is 1000 and n minus 5.5, so that I get random patterns of +1 and -1. Let us assume that the energy per bit is a unity. And I initialize now that I have generated a bit sequence, and because these are Gaussian signals of unit variance, so I safely assume that EB is 1. And now I have to generate a Bpsk mapper. So here I create a symbol vector. I initialize a blank array for a signal symbol vector. So each symbol is either a e raised to j0 or e raised to j pi, which are nothing but plus root EB or minus root EB. So what I do is I write a for loop in the range 0 to len b vector. if the bit is a 1, if the bit is a 1, my symbol is I say that some variable simb is root of EB. That is, if it is a 1, it is a root of EB. Or else if it is a -1, simb should be minus square root of EB. And every time this simb is appended to my simb vector. Now, the sim vector contains my symbols, my baseband Bpsk symbols. Now, I plot the real part of it against imaginary part, but it is generally written that here it is e raised to j0 and e raised to j1, e raised to j0 and e raised to j5, which are +1 and -1, so there can't be any imaginary component. So, I plot this, then I save that figure with some name, and then what I do is I add additive white Gaussian noise to that. So I generate a noise, I initialize a noise vector, a blank 0, a blank array, blank Python array, then I assume that the noise variance is a 0.1, and for the length of simb vector I add a noise to this, a complex random noise to each vector, each symbol, I add some noise variance. Then I plot the signal constellation. And now let us run this code, and I run this code with interactive Python, and let us run this code, run bpsk const.py, and you can see that these are the two windows popping up. This is my signal constellation, one at plus root EB, because I assumed EB is 1, so it is one vector is coming here, one signal point is coming here. This is my S1, that is at +1, and another point is coming here. This is corresponds to my S2, that is at -1. It is nothing but minus root EB. So this we are getting the expected Bpsk signal constellation with Python codes. Now let me close this window and let me see the other window. This is the effect of noise. This is the effect of noise. You can see that the original constellation is blurred with the noise. Earlier it was at this point 1, but it can be anywhere here. You can see that the constellation is blurred with additive white Gaussian noise. And here also the one at minus root EB or -1, that's also blurred very much. But here also my receiver can receive this fairly well, because if you see here, this is my decision boundary. If the signal is above 0, I can say it is a logic 1, and if the signal is below 0, I can say that a -1 or a logic 0 is transmitted. Here it is possible because the noise is not that much affected. It's the noise variance I assume to be 0.1. Now let us see. Now let us increase the noise variance and see how the error happens. Now I go back to my code. I make it instead of 0.1, I make it a 0.4. Say. Now run this code again. You can see the effect. Now you can see that the constellation is without noise. There is no change. It is the original thing, but with the noise, if you say, you can see that the constellation has been blurred a lot. Some symbols corresponding to +1 must be falling below 0, and some symbols corresponding to logic 0 must be falling in the region above 0. So there is always a chance of error. If you increase still further, say if you make it a 0.5 or 0.6, let us make it a 0.6 and save this file, and I run this again. Now you can see that the whole constellation is blurred. It comes as a single block. One can make out easily which signal is being transmitted, whether it is a logic 0 or a logic 1. So now we have to understand the probability of error. Now let me go back to my presentation. Now this is the effect of AWGN. This we have demonstrated with Python codes. And here let us look at the probability of error. So in the first video I told you that, and in the class also I told you that the probability of error, if two signals are given, a single constellation is given, that it is q d by 2 sigma. What is d? D is the distance between the two signal vectors, and sigma is the, what is sigma? That is a noise standard deviation of the noise. Here it is root n naught by 2. But if you go back to what is that d, let us go back to this and look at that. What is the distance? These are the two signals S1 and S2. What is the distance between them? This is at minus root AB and this is at plus root AB. So what is the distance between S1 and S2? It is 2 times root AB. So if that is there, the derivation is pretty simple. If you come here, this is a q, p is q d by 2 sigma, which is nothing but q d is nothing but 2 times root eb divided by 2 times root n naught by 2. Why? Because the standard deviation is root n naught by 2. So these two are cancelled and this 2 goes up, so it becomes q root 2 eb by n naught. Some people express this in terms of the error function, complementary error function also. I have a relation q of x is half error function complement x by root 2. So by that I can write this as half error function complement root eb by n naught. Okay. I will say this again for you. This is P is q d by 2 sigma. D is, what is d? That is the distance between the two signals. It is q 2 root eb by 2 root n naught by 2, because sigma is root of n naught by 2. N naught by 2 is my power spectral density. So here it is q root 2 eb by n naught, or that is half error function complement root eb by n naught. You can see that a half has come and this root was gone, because qx is half error function complement x by root. So you have derived the probability of error for a Bpsk constellation of Bpsk system. Now let me summarize with whatever you have learned or whatever objectives you have met. You understood the mathematical model of Bpsk. Then you understood the Bpsk single constellation and the effect of AWGN on that, and you demonstrated with Python code. And you derived and understood the probability of error for Bpsk system. So with that, let me summarize in this video. Bye bye.